Welcome to science class, which today comes from my living room. Today we're going to learn about matter and minerals. And so this begins our study of the geosphere, the solid body of Earth. Matter has certain properties, and those properties are reflected in minerals, which are the building blocks of Earth's lithosphere. The most striking example of this is the wonderful crystal geometry that minerals possess. This crystal geometry is completely dependent on the nature of how the elements and atoms which make up a particular mineral bond together. But the first part of this discussion will be about the nature of matter, especially chemical bonds. If we are going to hope to understand how physical stuff works, well, we have to know what physical stuff is. Let's get started. As I stated a second ago, the first part of this discussion is on the nature of matter and how matter interacts with matter. Atoms are the building blocks of matter and are composed of protons, which have a positive charge, neutrons, which are neutrally charged, and electrons, which are negatively charged. All of the naturally occurring atoms on Earth have a name. We call them elements. A single atom of gold and a kilogram of gold have exactly the same physical and chemical properties. Physical properties maybe don't apply so well to the individual atom, but whatever. A gram of gold and a metric ton of gold have exactly the same properties. Look at the periodic table. Find an element. The whole number that corresponds to its position is its atomic number. Every gold atom in the universe has 79 protons, and that's it. Imagine if we had a block of gold sitting here and we somehow added a single proton to every atom in the sample. What would happen? The entire block would immediately become mercury, all of it. It would go from a solid, shiny, yellow, dense metal to a liquid, silver, shiny, dense metal. Neutrons contribute to the mass and density of an element, but that's essentially it. There are isotopes of elements, variations of the same element which have the same proton number, but varying numbers of neutrons. Some of these isotopes can be radioactive, a process that will become important much later in the course. The chemical properties of an atom are determined by their electrons. When we say chemical properties, we really only mean how elements react with other elements by virtue of chemical bonding. When two atoms bond, they become part of the same molecule or compound by distributing some of their electrons. The two most common types of bonds are covalent and ionic bonds. In covalent bonding, 1, 2, or 3 pairs of electrons are shared between atoms. Covalent bonds produce molecules, and these can be solid, liquid, or gas at room temperature, but ultimately will have relatively low melting points. Water, atmospheric oxygen, and sugar are examples of covalent molecules. Ionic bonds form between ionized atoms, which means they have a positive or negative charge. In isolation, any atom is chemically neutral. Their proton and electron numbers are equal. Only when atoms start interacting with other atoms do they become ionized. To negatively ionize an atom, give it 1 or 2 electrons. To positively ionize an atom, remove 1 or 2 of its electrons. Remember, we cannot add or remove protons because that would change the element, and the nucleus is not a factor in chemical bonding. Ionic bonds are very strong, and all but a very tiny class of ionic compounds have melting points of several hundred degrees Celsius. 800 degrees, in fact, for sodium chloride. That name, sodium chloride, that means we have a substance made of sodium and chlorine. Sodium is a silver, shiny, highly reactive soft metal. You can see here that you can squeeze it like a gummy bear left outside for a day, and it cuts just as easy. Sodium also becomes molten and even can explode when placed in water. Chlorine? Well, it's a green toxic gas with a highly distinct odor. Individually, you would want neither of these elements anywhere near you, but together they form a useful compound. When 2 or more different elements chemically combine, they become a compound. Almost without exception, compounds have vastly different physical and chemical properties than the individual elements which they are made of. And we can see that in the minerals that make up our lithosphere. I want you to guess what the most common element in Earth's lithosphere is. I told you iron is the most common element in Earth, but almost all of it is in the core. So imagine you are walking on a bare rock formation. What is primarily beneath your feet? It's actually oxygen. A whopping 46.6% of the lithosphere is oxygen, followed by silicon, which is 27.7%. Aluminum is 8, and iron is 5. Calcium, sodium, magnesium, titanium, and hydrogen round out the top 10. But nowhere on Earth will you be able to find these things in elemental form. They always form compounds. Certain geologic processes can deposit relatively pure veins of precious metals, but these are extremely rare exceptions. You can't even see the majority of gold that's mined. A ton of rock won't yield much more than a gram of gold. Almost all of the iron we use in building structures, which is around 230 billion tons annually, comes from banded iron formations, like these ones in Australia. This is actually rust, iron oxide, which is a mineral, and it formed billions of years ago when organisms first oxygenated the atmosphere through photosynthesis. It takes around 800 billion tons of ore to yield those 230 billion tons of iron. Like I said before, compounds contain radically different properties than the elements that they are made of. The granite peaks of Yosemite National Park and the Black Hills are composed of around 40 to 50% oxygen. Weird, right? Let's look at a mineral, pyrite. If you had to guess what's in it, you'd maybe say gold or copper or maybe brass, which isn't an element, but its color is similar. In fact, pyrite is made of 1/3 iron and 2/3 sulfur, none of which is really anything like pyrite. So who cares about minerals and their composition? Well, you should. Okay, I admit, is it important that you pay attention to the composition of the lithosphere in the soil? No, you don't need to, but the world you live in exists because of that. The United States is a global leader in producing food, oil, coal, iron, aluminum, and many other things. And you know where all that stuff comes from? Yup, right out of the ground. All of the raw materials, we've got them. So we really don't have to worry about any of it. Nobody ever stops to think about this because, well, you don't need to. And, you guessed it, it was built by the work of engineers and scientists and many others who put all this infrastructure together. A good science education should produce an understanding of scientific concepts, but I also feel we need to emphasize the importance of all of this and how it has improved our lives. It's hard to appreciate something that's mostly invisible. Back to minerals. In the next video, we will cover where minerals come from, but for now, I just want to talk about some of the most important minerals and elements. What the heck does important mean? Well, iron is important because if our planet had none, it couldn't generate a magnetic field, and our atmosphere and oceans wouldn't exist, and life couldn't exist. But I'm going to be selfish and talk about minerals that are important to civilization. We could start with iron, though. Iron is used to make steel, without which apartments or office buildings over 10 to 20 stories tall just aren't feasible. Steel is tremendously strong and flexible and lightweight, compared to other things, that is. An entire skyscraper can actually weigh less, oftentimes, than the bedrock that is excavated for its foundation. No steel, no vertical skyscrapers, no megacities, no mass-produced cars, no, well, a lot of things. After water, concrete is the second most consumed material on Earth. Concrete is a mixture of aggregate, which is simply small pebbles and sand of any composition, and cement. Cement is a mixture of calcium, silicon, aluminum, iron, and a few other things. Gypsum, a very soft and common mineral, is a major source for these elements. Can you imagine a day without electricity? It shouldn't be very hard. The first electronic device was the telegraph, and that's only been around since 1835. And commercially available electricity has only been around since the 1870s. But I bet most of us use more electronic devices than non-electronic devices. The alarm you woke up with this morning, the toothbrush you hopefully used this morning, the stove or microwave you made breakfast with, the vehicle you go to work or school in, the dopamine regulating brain slave rectangle you spend 3 to 4 hours a day staring at, the computer you do your homework on, the other dopamine regulating brain slave rectangle you spend 3 to 4 hours a day staring at, Even our refrigerators have LCD screens and Wi-Fi. Why are we doing that? All of these things either are electronics or wouldn't work if their electronics were taken out. But 150 years ago, nobody had electronic versions of any of those things. None of them are possible without silicon for computer chips, lithium for batteries, or copper to conduct all of the electricity. Before computers, silicon was mostly useless, although it makes up over 25% of Earth's lithosphere. Copper is used as roofing material because it's common and flexible. The Statue of Liberty is made of copper. It used to shine like a new penny. Then there are seemingly strange trace elements in minerals that we really don't think of, such as molybdenum, which helps clear our bodies of sulfites. You need raw iron in your blood also. Food that is fortified with iron has, literally iron in it. It's powdered and in small amounts, so don't worry about it. But you could extract it with a magnet if you ground your cereal into powder. As we learned a few videos back, the geosphere is connected to all the other spheres. The individual atoms and molecules in your body were once in separate parts of Earth's crust or part of other organisms. So we know what Earth is made of. Here those things are again. But what about you and me? Well, here it is. This really isn't a very close match. Your body is not made of the most common things on Earth's surface, but the foods we eat come from the soil, or they eat organisms that come from the soil. What's happening? Well, we don't have the whole picture. Remember, nothing is as simple as it seems. On Earth, we have what are called biogeochemical cycles, matter cycles between all parts of the Earth. The atmosphere is a huge part of this. That's where all the nitrogen and carbon comes from. Hydrogen and oxygen, it's in the water and in the air. Other trace elements like sulfur, sodium, chlorine, magnesium, iron, those are more or less evenly distributed throughout the surface. It sounds strange, but remember, we're only requiring very minute amounts of the stuff, so even if we can't see it, it's still there. Animals that live around reefs require certain levels of calcium and carbon to build their shells. Just as you need calcium to build a proper skeleton, they need it to build a proper exoskeleton. The incorporation of minerals within the bodies of living organisms was a gigantic evolutionary step. Teeth, bones, shells, exoskeletons, these characteristics were part of the driving force for the Cambrian explosion and the rapid diversification of different animal phyla. Robert Hazen has theorized that organisms themselves were the driving force behind mineral evolution. The 20% oxygen in the air, that comes from photosynthesis. Earth has plenty of water, and in the light-dependent reaction, oxygen is produced from that water. Oxygen is extremely reactive, but not when it's already bonded to other elements. Distributing that oxygen globally into the atmosphere allows for it to react with several different materials. Oxygen is the most common element in the lithosphere, and therefore in minerals as well. Today there are around 4,300 classified minerals, but early in Earth's formation, Hazen theorizes there are perhaps only 250 minerals that could be formed by regular geological and hydrological processes. This means the vast majority of minerals exist because life supplies the ingredients. That's mineral evolution. Minerals and life are codependent. That's quite an amazing idea. Next time we will cover the geological processes that form minerals and how geologists use that information to interpret an area's history. Thanks for watching.